for Fourier series. I view Fourier series as a way to represent functions and signals. But more importantly for this course, Fourier series is sort of a prerequisite or one of the topics you need to know in order to solve partial differential equations in the next fourth module. Okay. So in both contexts, it is quite important, interesting as well. And we'll try to do this. It involves a lot of integration. So for the second exam or the moving forward, if you keep a table of integrals with you, it might prove helpful to you. Like a table of standard integrals, if you have this ready, you can save some time. Okay, that's just a tip. All right. So Fourier series starts with the idea of what are periodic functions. What are periodic functions?
Periodic outputs or
What do you mean by periodic output?
it's the same output after several times. Yeah, you can take that.
So if you go forward in time, but if you go exactly a certain amount, you come back to the same value of the function. Or if this is written in space domain, we'll use the symbol x, where p is the period of the function. Okay, it can be any function. We typically associate this with trigonometric functions. Say suppose you had a function. I intuitively draw a periodic function. So you had something that goes like this, a triangle waveform. But if we start defining the function such that it is just an infinite sequence of repeating triangular waveforms, we would say it is a periodic function. Okay. Now, the main goal of this Fourier series idea is to represent periodic functions in terms of trigonometric functions sine and cosine. To represent a periodic function in terms of trigonometric functions, because trigonometric functions are inherently periodic. And can be used as units to construct or represent any function. So we write that as f of x equal to a naught plus infinite series n equals 1 to infinity an sine nx plus bn cos n. Sorry, I got it backwards. This is an cos nx and bn sine. This formula is valid for functions which have a period of 2 pi. T equals 2 pi. Okay, and the coefficients a naught, an, bn are called Euler formulas are given by either formulas. Where A naught is 1 over 2 pi will, I'm just throwing this formula at you, but one or two lectures down the line, we'll see where these formulas come from. It's a little non-linear in narration, but first we'll see the formulas and then understand their origin story. Okay? An is 1 over 2 pi minus pi to pi f of x cos nx dx, and n varies from 1, 2 and so on. Dn 1 over 2 pi minus pi to pi f of x sin nx dx, n equals 1, 2. This is for a period of 2 pi. We just start with that because that somewhat simplifies the formula. If we consider any function f of x whose period is p equals 2l, where l is a arbitrary length of length in the domain x, that in that case we would write f of x still is equal to a naught plus summation n equals 1 to infinity an cos n pi x over l plus bn sin n pi x over l. And again, these formulas will be slightly adjusted to write a naught equals 1 over 2l minus l to l f of x dx an equals 1 over 2l minus l to l f of x cos n pi x over l dx, and bn equals this is the one of the more basic formulas that you will learn and use in this topic. Obviously, since we all are familiar with integration, if I tell you f of x is given by x squared e power minus x or some logarithmic function, for you to do the integration and then expressing it as a infinite series or a Fourier series is doable. Would you agree with me? In principle, we all know how to do integration, and you would do that and represent that as a power series. Okay. This skill is needed specifically when we look at partial differential equations of the form. Let's say if we are trying to solve partial t over partial x squared plus partial t over partial y squared equal to 0. Suppose we are looking to solve equations of this form. The solution t of x comma y is going to be a double summation, which is say for example, it is going to involve sine and then cos terms, which are themselves Fourier series. So this basic skill is needed when we do problems of partial differential equation in Cartesian domain. So I'm telling you why we are learning. Okay. So if I give you an example from the book, we select an example and say we want to do e power x, represent e power x as a power series. Just to get some practice here, we are going to start with that function. Consider f of x equal to e power x. Consider f of x equal to e power x with a period p equals 2 pi. The period p equals 2 pi. First of all, how to represent this f of x and how does it differ from the function e power x in general? Kindly answer this question for me. How to represent this function? This is the function. What is the difference between this function and e power x? Okay, how will you represent it?
Location.
Let's say we start with first the interval minus pi to pi. In this interval, how does this function look like? It varies from e power minus pi to e power pi, and it crosses 1 at x equal to 0. So this is x equal to 0, at which this is 1. And approximately, can somebody tell me how much is e power minus pi? Should be a very small number, close to 0 probably, like 0.01 something.
0.04.
0.04, let's say it's somewhere here. So here is e power minus pi. And how much is e power pi?
23.
E power pi. So it's a function that looks like this. This is f of x with a periodicity of 2 pi. So if I plot this again from pi to 3 pi, this is just going to be repeated. That is the difference when we say a periodic function. You can define the function with any periodicity, or you might encounter the function with any periodicity, and it just repeats infinitely. If we in general say the function f of x, that would just be to start at so let's say very large values of negative x. It goes like this. That would be e power x in general. So the subtle difference is we curtail the function at an initial interval and then repeat that template infinitely. Okay. So now let's go forward and yeah.
From pi to 3 pi, it will start from the previous value.
Yeah, this is going to be repeated.
If I will write e to the power of minus pi, it is 0 point something, 0.4.
Yeah.
But e to the power pi is a bigger value.
Yeah.
And again, if I will start from e to the power
There is a discontinuity here. There is a discontinuity here because it is being made into a periodic function. When you take a waveform or when you take a function, it is piecewise continuous, but at the edges of the interval there is a discontinuity. So when I say discontinuity, what do you understand?
there is some breakage. It is
It is like if you take the left hand limit That is, if I calculate what is f of x approaching pi from the left side, I'll put that as pi minus. That is not equal to f of x approaching pi from the right side. That is the discontinuity. So the value of the function, of course, and also the derivative will be discontinuous. It's the same idea when you write a triangular waveform and you repeat this again and again and again. What's going on here? It's continuous but not differentiable. Because the slope, if you approach the slope from one side, the slope is here negative, but if you approach from the left side, it is negative, but up from the right side, it is positive. Right? So at these points of periodicity, you could have either discontinuities or what is the word for this? You could have loss of differentiability. I was at a loss of words. Loss of differentiability. Okay. So when we calculate these Fourier coefficients, the question for you is, in what interval are we representing this function using this expression?
Then you can try.
We are representing it in this original interval or any other subsequent interval. It is always between the intervals in which you do the representation, and then after that it's merely translating it from interval to interval to interval. So this representation is confined to this range. Remember that, minus L to plus L. And after that, periodicity is imposed upon the function. Okay. So shall we do this as an exercise just to get our integration chops going? Can you try, please? Do this integral where f of x is e power x 1 over 2 pi minus pi to pi e power x dx. Can you tell me a number, like the value? E power pi minus e power minus pi divided by 2 pi. So if we start here and we do some examples, that gets you that necessary speed during the exam. Are we all comfortable with integration by parts? Have we used it recently enough to? So if you have, tell me if I'm off about this. If you have integral u dv prime, this is uv multiplied by u dash v dx. Integrate the first function minus integral of derivative times the value of v, sorry, d of v, u dash v dx. So we'll get one right example here. So what is an? 1 over 2 pi minus pi to pi e power x cos nx dx. A very, yeah. So this is 1 over 2 pi e power x. What is integral of cos nx? Sin nx divided by n. sin nx divided by n, and that is applied between minus pi to pi. Minus integral minus pi to pi e power x, that is derivative of e power x happens to be e power x times sin nx dx. There is still this 1 over n, which I'll write 1 over n here. So 1 over 2 pi e power pi sin n pi minus e power minus pi sin of minus n pi divided by n. Am I doing this right? Yeah.
But in my part, we should consider e to the power x for v, right? As it means.
Sorry, come again.
Here there are two functions. One is exponential function and one is trigonometric function.
Right.
Yeah. So I think we should consider the last function, the exponential function, as the Elliott rules.
If you mean this just like if you first integrate this couple of times, you will end up with an on the right side, which will eventually how we will end up in doing the integration. If you keep integrating this, leaving this, maybe let itself play out. Maybe if I'm wrong, we'll go back and do the other. Okay, let it play out. What is sin n pi? You know sin x, right? Sin x is if you have sin pi x, or if you have sin 0 or pi or 2 pi, doesn't matter, n pi, sin n pi is always 0, regardless of what value of n you have. The other property of sine function is sine of minus x is minus sin x. It's an odd function. Right? So this sin n pi is 0 because of being sin n pi, and this sine of minus n pi is nothing but minus sin n pi, again 0. Minus 1 over n minus pi to pi sin e power x sin nx dx. By the way, anybody has this function value for the a naught?
3.68.
3.68. Can you give me 4 decimal points?
3.676. 1.
Thank you. Okay, so the integration continues. An is 1 minus 1 over 2 pi n minus pi to pi e power x sin nx. Some of you might have already done this, but I want to take the time to do a few steps initially. So what is this? Minus 1 over 2 pi n e power x. What is the integral of cos x? Sorry, integral of sin x, sorry. Minus cos nx divided by n, and that you have to apply between minus pi to pi. Okay, plus 1 over n minus pi to pi e power x cos nx dx. So something interesting is happening. I think, minus 1 over 2 pi n. This is with a negative sign, so I'm going to write negative e power pi cos n pi minus e power minus pi cos minus n pi, the whole thing divided by n, plus 1 over n minus pi. Okay, do you recognize this? This is an, right? This is an times 2 pi. This right here is 2 pi times an.
Original, it's supposed to be the end on the
N
top.
square. Sorry?
On the top, it says A, and it should be, you're using.
No, I'm just saying I'm going back here. If I multiply the 2 pi on this side, this integral alone is nothing but 2 pi times an, which is what I did here. Wherever this integral appeared, I replaced it with 2 pi an. Yeah,
In the first place, like, yeah, there is a formula for integral of to the power ax plus cos b. So can we not apply that?
if you have a table of integrals in which this integral is given, by all means use it. So I welcome every one of you to bring a table of integrals to the exam, or even to class, keep it with you to speed up things. But I just wanted to do this because some of us might have not done this in the recent past. So to, get back in the game. Okay, so what is this? What is cos n pi? Sorry? So cos 0 is 1, cos pi is minus 1, cos 2 pi is 1, cos 3 pi is minus 1. You know these. So how will you generalize cos n pi? Power n, right? So this is minus 1 over 2 pi n. I have another negative sign, I'll still keep it. Minus 1 over n e power pi minus 1 power n minus e power, sorry, this is getting cluttered. So I have an equal to minus 1 over 2 pi n minus 1 over n e power pi minus 1 power n minus e power minus pi minus 1 power. So what is cos of minus n pi? What is the property of cos function? It is a even function. Cos x or cos of minus x is also equal to cos x, which is an even function. So this would still be minus 1 power n, the whole thing, close the brackets, plus 1 over n times 2 pi an. Minus 1 over 2 pi n. I have minus 1 power n plus 1 divided by n e power pi minus e power minus pi plus, so I'm going to get this n outside, n squared. I have plus 2 pi an, or this is 2 pi an, this is 2 pi n squared. I have an equal to minus an over n squared multiplied by, sorry, minus, or I'll say plus, minus 1 power n plus 2 times e power pi minus e power minus pi divided by 2 pi n squared. Did I make some mistake?
So it was the first, on the first one, it's -1/n.
Yeah, so I clubbed that minus sign along with this and wrote -1 power n plus 2. And then I still have this. I have 2 pi n squared. Okay. -1 power n plus 2 is the same as -1 power n because the -1 squared is just irrelevant. Okay. And then I have an equals 1 over 1 plus 1 over n squared multiplied by -1 power n e power pi minus e power minus pi divided by 2 pi n squared. Or this is 1 over 1 plus n squared minus 1 power n e power pi minus e power minus pi divided by 2 pi, or I'll compactly write this as, do you recognize this function? Like a shorthand. Hyperbolic sine of h is e power x minus e power minus x divided by 2. Okay, so we'll write an equals -1 power n 1 plus n squared hyperbolic sine of pi divided by pi. What is your immediate observation when you look at such a formula with -1 power n, where n runs from 1, 2, 3 and so on? You have it, tell me. It's going to be alternating values will be negative and positive. Right? This is a positive number, this is a positive number, positive number. An will have alternating signs. Odd terms will be negative and even terms positive. Simple. So, all right. Can you go ahead and compute B naught or Bn? If you have that integral, Manoj, right?
Yes.
You have that integral for this. Can you help us save time by reading it out?
So, e to the power x.
Okay, e to the power x.
E to the power ax plus e to the power ax sin bx dx is equal to e to the power ax by a square plus b square into a sin bx minus b cos bx
A sin bx.
minus, yeah.
This thing is multiplied with both or only
Yes, both. Plus,
plus into arbitrary function.
yeah.
Okay. Then, so if you had a table of integrals with you, you could just pick out this, apply the lower limit and upper limit and evaluate. I of course didn't remember this or didn't know this, but I still wanted to go through the integration. I still would like to get this final answer so that we can represent the function as a power series or a infinite series. Can you get me this? I would, including myself, I would opt for doing BN again and getting that practice in, because we are going to do this a lot. It's good to get some practice. Okay. So I'm going to do this quietly. you can also try and then let's compare our answers. Am I doing this right? So I'm getting -1 power n plus 1 2 times divided by n squared over n squared plus 1, 2 minus 1 power n plus 1, sine h. Doesn't look symmetrical, so that raises a suspicion for me. Right. Are you getting this? No? What are you getting?
N times minus 1 to the power n plus 1,
Okay.
simplify parabolic of p
Oh,
over,
oh, right, okay.
yeah, over 2 pi times 1 plus n, no. In the denominator form, there should be some times 1 plus n s squared. No, n squared.
1 plus n squared. Okay, are you getting this? Or that? Are you getting this expression or the other expression or any third choice? Okay, are we confident about this? Can I erase this part? Okay, so let's okay, let's do this together. Let's see what we are getting. Bn equals 1 over 2 pi minus pi to pi e power x sine nx dx. 1 over 2 pi e power x cos nx divided by n from minus pi to pi. Is this correct? Yeah. Minus 1 over n minus pi to pi e power x cos nx dx. Okay, so this is e power pi minus e power minus pi divided by n times minus 1 power n. Is this correct? I would ask you to please do this because this is the kind of stuff you'll be doing in the exam also. Is this correct? Yeah, okay. So then minus 1 over n. This is e power x. What is the integral of cosine? Integral of cosine is sine, right? Sine nx over n from minus pi to pi minus 1 over n minus pi to pi e power x sine nx. Wait, yeah, e power x sine nx dx. That is e power x derivative happens to be e power x. Are we good so far? Yeah. If you look at the middle term, sine n pi, sine of minus n pi. Both ways, this term just goes away. Okay, so 1 over 2 pi. Okay, so this is 1 over 2 pi. Can I write this 2 hyperbolic sine of pi divided by n times minus 1 power n? Can I write it that way? Yeah. Then I have plus, because this is a negative sign here, and then there is a negative sign here. I have plus 1 over n squared. This is nothing but 2 pi times bn. 2 pi times bn. Are we getting the sign correctly? We didn't make any mistake there. Integral of cosine is, integral of sine is cosine. Isn't this minus cosine?
Yes.
Right? So there is another negative sign, n plus 1. I guess that purely because I know this Bn, when it goes to the other side, cannot be appearing as 1 over n squared minus 1. That creates a singularity at n equals 1. That can't be true. So that is your thinking, okay? So what I'm going to write is take out one negative sign and write this as minus, and I will check this. Okay, so if there's a negative sign here, this becomes positive, this becomes positive, so this becomes negative. Minus 1 over n squared. So this is 1 over pi sine h of pi divided by n minus 1 over n squared bn times minus 1 power n plus 1 . So I have bn times 1 plus 1 over n squared equals minus 1 power n plus 1 sine hyperbolic of pi divided by n pi. Divided by n pi. So I would have bn equals n divided by 1 plus n squared minus 1 power n plus 1 sine hyperbolic of pi divided by pi. So it's almost the same, except it differs by a factor of minus n. So minus, okay, I'm going to write this to minus 1 power n for comparison's sake. I mean, so I'm going to write this as 1 over 1 plus n squared times minus 1 power n sine hyperbolic pi over pi. Whereas bn is n over 1 plus n squared minus 1 power n sine hyperbolic of pi divided by pi. This is also sine hyperbolic of pi divided by pi, which will give a symbol. We'll call it like a naught. I mean, it is a naught, so I'm just going to keep it as a naught, which means I can write an equal to, or an equal to a naught times minus 1 power n 1 plus n squared, and bn equals a naught times minus 1 power n times n, or times minus n divided by 1 plus n squared. So finally, what is the Fourier representation? e power x in the interval minus pi less than x less than pi is equal to a naught times 1 plus summation n equals 1 to infinity. What is an? An is minus 1 power n, 1 plus n squared cos nx plus bn, which is minus 1 n plus 1 n over 1 plus n squared sin nx a naught is sin hyperbolic pi divided by pi. Kindly expand and write a naught times 1. What is the first term in this series? Minus 1 power 1 divided by 1 plus 1 squared. So this is minus half cos x plus, what is this if you substitute n equals 1? That is 1 over 2 sin x plus second term n equals 2 positive 1 over 5 cos 2x minus 2 over 5 sin 2x plus and so on up to infinity. Okay, that took us a while. You have this representation. Now what? How can we interpret this representation? It's like saying in this interval, e power x is same as this series. So what does that mean? It's a hard question. How to interpret this representation? Because you are all coming from dynamics or vibrations or signal systems or waves. You encounter periodic functions and signals in many places. When I say that a function like e power x can be represented in terms of periodic functions or trigonometric functions, so what? What is the implication of that? You just know the answer and won't tell because I trying to give you a tough time with the exams. Is that it? Okay, let me try to help. E power x is, you can write an infinite series 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus and so on up to infinity. Suppose I ask you to approximate the function. You do make a very crude approximation and say e power x equals 1 plus x. That's the approximation you come up with. You're writing, let's call e power x approximately same as 1 plus x. Under what conditions that is not a bad assumption or a bad approximation? X is nearby 0. X is in the vicinity of 0. It's if x is small, this is not a bad approximation to run with. If x becomes large, it becomes progressively bad. To come up with a better approximation, what would you do? You would add more terms. If you add more higher order corrections, if we start viewing this as like a first order correction, if you add a second, third, fourth order correction, the function or the approximation of the function becomes progressively better. Would you agree with me? So if you are you're trying to approximate a function and you want simplicity, but not too much simplicity, meaning you want to represent it with as few as functions that are necessary to reasonably represent it. You can in principle add like 500 terms and make it very accurate, but it's besides the point because you don't need that much level of precision. So if you add 3 or 4 terms, whatever your range of interest is for x, in that range, if it is accurate, you call it. You say, okay, good, this is good, good enough. Take that thinking and apply it for this approximation. This is in terms of individual powers of x. This is in terms of functions of x, which are periodic themselves. What is the periodicity of cos x and sin x? 2 pi. 2 pi, right? Their period is 2 pi. What is the period of cos 2x or sin 2x? Pi. What would be the period of cos 3x and sin 3x? You know the sequence. You are increasingly representing the same function with a basic frequency, a half of that, a third of that, a fourth of that, progressively higher frequencies or smaller periods. So what? Now interpret this for me. In terms of
Different frequencies.
you are representing it in terms of different frequencies. Can we say that? What is the frequency of 1? Or in other words, its period is infinity, meaning if you have a function that is a constant, you can sort of abstractly say at infinity it repeats, which doesn't make much sense. You can just say its period is infinity or frequency is 0, frequency 2 pi, pi or 2 pi by 2, 2 pi by n in general. Okay. All right. So now you are in the lab. You are a signals engineer. A mechanical engineer is sort of everything in different roles. You want to construct a waveform and show it on the oscilloscope that looks like this e power x. If I ask you to construct it with these frequencies, and you have signal generators that can make waves of, let's say, this 2 pi radians per second. That is your frequency, sorry, 2 pi radians, or you have something that can do at 1 hertz, half hertz, 1/3 hertz, 1/4, 1 over n, and so on. Now, what does it mean to look at this series and look at this function? If you just took the first 2 frequencies, you add a DC voltage, and then you add a frequency of 1 hertz. This function is sort of like a first order representation of your targeted function. If you include one more term, it is adding a second order correction, third order correction. After maybe 5 or 6 frequencies, it is not necessary that you have to include many more. You can just stop there and that will reasonably approximate e power x. Same analogy, just take the words I just said. If you are a musician, you have, let's say, 4 frequencies. The the fundamental frequency, first overtone, second overtone, third overtone. If you add them up in the right proportions, you will end up with one function, which is the music you are seeing. What is the role of these coefficients? These AN values. What is the role of this AN Dn and A naught.
They amplitude contribution, basically.
Weightage, amplitude or weightage of each frequency. It's like you are the musician, you know how much, in how much tone or not tone, how much intensity you should play one frequency and the other frequency and mix them in the correct proportion, so to speak, right? So that is the amplitudes, okay? The in many fields of wherever time domain analysis is done, or even periodic functions are analyzed, we approximate this as an infinite series. For analytical computation, we treat it as infinite series. For numerical calculations or approximations, we consider what is called as nth partial sum, or I'll say n partial sum. So if I say f of x equal to a naught plus summation n equals 1 to uppercase n an cos what was the formula I had for arbitrary intervals? N pi x over L. N pi x over L. Pi x over L or 2L? Yeah, L plus Bn sine n pi x over L. This series is not an infinite series. Maybe make a note. Not an infinite series. It is called a nth partial sum. Okay. How big should n go? How will you arrive at that determination? Should we do n equals 4, n equals 10? Where to stop?
So like a target goal, I want to correct to the sixth digit.
So if I say the let's say if I have f of x evaluated using the nth partial sum minus f of x evaluated using the actual function, if I want this to be at less than a certain tolerance, I will target that tolerance level and keep adding more sums or increase the order of the sum until that tolerance is met. Okay, so that is the idea of nth partial sum. So where is this going to be useful? If you are trying to reconstruct signals, like if you are measuring something and later you have to mathematically reconstruct it, you first try to work out the Fourier series and then use the partial sums to reconstruct the signal. Okay. So this is briefly touched upon in section 11.4, which also talks about what is called as Parseval's identity. I want you to be aware of this nth partial sum idea because in practice it would be really useful, but it's not something I plan to include in the problem solving. So I made my point that it is related to reconstructing signals, and that's about it. I won't go further. Okay. I told you that we'll try to understand where these formulas came from after discussing one concept. So I'm just going to start on that. I don't think I'll have time to finish it today. We are going to see what is referred to as orthogonal functions. So I'll talk about orthogonal functions. This is section 11.5. Okay, orthogonal functions. Functions, something I'm going to repeat from the book. Functions ym of x and yn of x are considered to be orthogonal functions if ym of x multiplied by yn of x multiplied by rx of x, r of x times dx between a to b, integration between a to b should add, are considered to be orthogonal in the interval a to b if this integral is 0 for any r of x that is greater than 0. For any r of x greater than 0 when m is not equal to n. If you have two integers or two values of m and n, which are distinct, these two functions are said to be orthogonal if their integral is 0 for an arbitrary weighting function. We call this r of x as the weighting function is like your amplitude, like your amplitude. Okay, the simplest example we can think of is you can take sine mx and sine nx where m is not equal to n. Try doing an integral of this from say 0 to pi, where we are considering r of x right here to be 1. Regardless of what a and b are, you will usually find that this integral is 0 if m is not equal to n. Example. All I'm doing is introducing the idea of orthogonal functions, which are defined in this way. Okay. If you take your trigonometric functions, they are indeed orthogonal. You can verify that by trying this integration with Rx equal to 1. You will recover your Fourier formulas. Or you can try with Rx equal to f of x, you will recover it. Okay, that derivation we are going to see in the next lecture. The key idea is when we did Fourier series, we are representing the function using a set of orthogonal functions. It is true that trigonometric functions are orthogonal functions. It is also true they are not the only orthogonal functions you can find. You can find out that if you take Jm of x times Jn of x dx from a to b, or let's say -1 to 1, this integral, this is also 0. Or in other words, your Bessel functions, your Legendre polynomials are also orthogonal functions. And just like we wrote a Fourier series in terms of trigonometric functions, you can write Fourier series in terms of Bessel functions or Legendre polynomials or combinations thereof. Okay, so our gateway or our path is to start with the very simple notion of representing functions using trigonometric functions. and then introduce the idea of orthogonal functions to generalize Fourier series, and then eventually write series in terms of any functions that you want. Where is this going to connect with us? When we do partial differential equations of cylindrical or spherical symmetry, you end up with either Bessel series or Legendre series. So that is where this is going to patch in. Okay. So you can't do the PD, the partial differential equation study, without understanding orthogonal functions and series representation using orthogonal functions. That is why, even though this definition, in my own view, is very obtuse, it just basically says it is orthogonal if you satisfy this. It doesn't say intuitively where this definition is coming from. And I'm not questioning that, like our engineering spirit. I'm taking the definition and understanding how to work with it. Okay, I'm also putting my ignorance in front of you, saying this is what I know, this is what I don't know, this is what I don't care to know. Okay, this is needed, I know it. I don't need to know where it comes from. Okay. All right. So we'll stop here and pick it up from next time. I did one very long example, but what I suggest you to do is to review sections 11.1 and 11.2 and 11.1 and 2. Do problems, that is, try taking functions, represent them as infinite series, get that practice. Okay. Let's not have two comprehensive finals, please. Let's have just one. Yeah.
Can you please upload the class recording in the weekend?
What?
Can you please upload the class recording?
Recording? Yeah, I'll upload it tonight or tomorrow morning.
Thank you.
Yeah. I think I've posted all the homeworks like at the start of the term. So you can start selecting problems and working them out right from today.